Thank you for joining me. I am Mr. Ish. I hope everyone's doing well. It's an interesting coordinate geometry video here. We have to accurately describe all the points in a pendulum swing. You can say a pendular swing, a simple harmonic motion that is represented in terms of the pendulum. How do you go about doing all of this? First, understand when you're looking at a pendulum, what you have here in terms of a representative swing would be something like this. That's what it would look like. Consider the fact that we have this attachment here, we'll call that the vertex. This right here is the ball, but it's generally and typically called a bob of a pendulum. There's a certain angle that it deviates away from the resting position. This right here, the central position, is the resting position where it is in a certain equilibrium at rest. We'll call that the resting position. When it deviates on either side by means of a certain angle, then it's in a movement. Everything is with regards to describing the points of a pendulum swing based off the deviation of this angle theta from the resting position. Keeping all of that in mind, also understand this, the vertex and the bob. If the vertex is attached at a fixed point and then the bob is made to rotate, it can rotate around and generate a circle. When you're looking at that, then the vertex is actually like a center of a circle, and then this right here, the stem of the pendulum actually becomes a radius. So in all aspects, this right here is a radius. When you're looking at these specific movements, you are generating sectors, and then this right here is also an arc length. All of this comes into play, but not all of it is coming into play for this video. I'm just saying in terms of a pendulum swing, these are the various attributes that come into play. In all instances, these are the specific points here on the pendulum swing. How can we describe those? Well, it all depends on how you position the vertex. If you position the vertex here above the origin and the bob is located at the origin, you'll have a different representation versus if the vertex is positioned at the origin and then the bob is located below the origin. And both of those instances we have to be looking at. We'll call this instance A, we'll call this instance B, and I'll show you in both instances what we have. Here's my representation A, here's a certain angle. Here's my representation B, a certain angle. Everything with regards to that angle. When we're looking at A, let's blow it up. We have a specific representation which generates like this. Here's my theta angle. You know this is radius, this is radius. You can look across and generate a right triangle. Here's an x dimension, here's a y dimension. This r dimension is located all from top to bottom. The vertex, the bob would be right over here. In this particular instance, when you're looking at the x, you have a sine. Sine theta is equal to opposite over hypotenuse, which is the radius. X will be equal to r sine theta. We're looking at a specific point or any of these points. These points are x comma y. The y value or the dimension, which will be from right here up to right here, can be determined by means of cosine. Cosine theta here is equal to adjacent over hypotenuse, y over r. Y is equal to r cosine theta. These are parametric equations. You've brought in a third variable, a parameter, a theta. Equations have x, y, and this parameter. These are parametric equations. In this representation, any of these points on this pendulum swing can be represented x comma y as this. The point will have x would be r sine theta, and the point y will be r cosine theta. In that I have demonstrated for you using right triangle trigonometry. Here the vertex is located above the origin, the bob is located at the origin. Now let's look at case number B. In case number B, the vertex is at the origin but the bob is located below the origin. And how can we go about looking at this? Well, let's draw the vertex, let's draw our bob, and let's draw a non-equilibrium position which is certain degrees away. Everything must be determined with respect to theta. Here's my arc length. What I can do in this particular case is use my reference horizontal as 0 degrees, and then I can generate a right triangle upwards, my certain dimension x, certain dimension y, and you know the stem of the pendulum is always a radius. If everything must be with regards to the resting position of the pendulum, and this is theta, then you know this right here is 90 degrees, and this angle right here must be 90 minus theta, and that's the angle you will use now for your right triangle trigonometry. Because when you pluck out that right triangle, you have an x, you have a y, you'll have this r, but this angle right here is not theta, it will be 90 minus theta. You have to understand this. Resting position of your pendulum, shifted the pendulum away from the resting position by theta degrees. I'm generating my right triangle by means of the reference horizontal, then this difference here is 90 minus theta. Now when I'm looking at the point right here, this is a point which has a certain x and a y to it. The x can be represented as this. You will be looking here at cosine and 90 minus theta is equal to x over r. Now when I'm looking at the y, it's with regards to this angle. I have sine 90 minus theta is equal to y over r. Cosine 90 minus theta is a cofunction identity which is equal to sine theta, and you know that sine theta is equal to cosine of its complement. Cosine of an angle is equal to sine of its complement. So cosine 90 minus theta can be substituted for sine theta by means of cofunction identity. Sine theta is equal to x over r, and now you know x is equal to r sine theta. X is equal to r sine theta. Look right here, sine 90 minus theta, its complement is cosine theta. This right here is equal to cosine theta, which is equal to y over r, and therefore y is equal to r cosine theta. And what am I getting? Am I getting the same thing exactly? Yes, I am. The x value is turning out to be r sine theta. The y value is turning out to be r cosine theta. So any point over here in this representation is going to be r sine theta for your x value and r cosine theta for your y value. No matter how you position your pendulum vertex, either above the origin or at the origin, the points on the pendulum are exactly represented in the same way as I've shown you. The x value is r sine theta, the y value is r cosine theta, and it's good. Just keep in mind here the cofunction identity came into play in case B. In case A, you didn't have the cofunction identity coming into play because you are working within that same triangle with the same angle. Here you're working outside this angle in a newly generated triangle with regards to a reference horizontal, so the cofunction identity comes into play. That's what I'm showing you here in this video. These are parametric equations which accurately describe any point in the pendulum swing. Have a good day. Bye.